Okay, so the rest of the semester, the way it'll go is today and probably Monday, we'll finish up computation. On Wednesday, I've left that open for kind of a review of the last module. But Friday, we'll go ahead and just cancel that class because the department holiday party potluck is going on. So I'll be here, of course, and available in Piazza if anybody needs any questions and stuff. But we'll just go ahead. We'll finish up before Friday. So once you've got assignment 10 in, which is due 1 week from today, that's it for the course. I'll have those graded as soon as possible on that Saturday. And that's the conclusion of the course. Make sure, I don't know, have you received an email yet about the course evaluations? Yes? They're open? Okay. Make sure that you're filling those out. And you know, leaving feedback. I won't see those, of course, until much later after grades have posted. So even though it's a smaller class, harder to be anonymous, it still is anonymous. So anyway, we left off last time talking about NP completeness. So here's our landscape so far, right? We've got deterministic polynomial time. These are the class of problems that are solved, or problems languages that are solvable by a polynomial time algorithm, deterministic in the usual sense. We then defined NP, which is the class of all problems that are solvable by a non-deterministic polynomial time Turing machine. Remember that a non-deterministic polynomial time Turing machine is one that has these two phases. It guesses a solution and then it verifies the solution. And if there is any computation path at all that accepts, the entire machine accepts. It's basically able to magically do all of this massively parallel stuff, but the resource measure is still the depth of the computation. And then we went on to define this area. These are the hardest of the hard. NPC is non-deterministic polynomial time complete, right? So NP complete problems. These are the hardest of the hard. And they're simply defined by everything in NP reduces to it, right? And that means that everything within NP complete also reduces to each other. In other words, it's basically a closed class. Because if you're complete, then you reduce to any other complete problems and everybody reduces to you, right? And the definition of, again, the definition of NP complete is that everything reduces to it, right? And there's no need to draw all these lines. All you need to do is come up with that first NP complete problem, right? That's the that was the original problem in the late 60s, 70s. You had to come up with this first problem, because once you've got that first problem and you've got this other problem, A, and you want to show that it's NP complete, all you have to do is take that one NP complete problem and reduce from it to your problem, and thus that implies that A is NP complete. Right? Yeah.
So does the deduction work both ways, or is it?
It works both ways for all NP complete problems, right? But that's simply by definition. Reversing it, you know, like coming up with a construction to actually reverse it, may be difficult. But the first one to the first problem here is that was the first one that was the most difficult, because once they've got that, now they can reduce to other problems. Now, does it work in reverse from, say, an NP complete problem down to a P problem? If you've got that, right, if L, NP, if, and this is a big if it reduces down to, say, sorting, then exactly, P equals NP. And you've solved the problem. We don't know that, right? Nobody knows that, and it's probably very, very unlikely. Right? So, no, does it work the other way? That would be extremely surprising, right? But this first problem, and I've got it here now. I was able to come up with a better LaTeX encoding for this. This is due to Cook and Levin in the early 70s. This is the canonically complete language. The canonically complete language is, given a machine M and an input X, then the double encoding of that thing, where M is a non-deterministic Turing machine, it'll accept X in a polynomial number of steps. This is very, very similar to the halting problem, which was undecidable. But why is this decidable? Because of this additional restriction here, that it has to accept it in a polynomial number of steps. If it goes beyond, if it goes exponential, super polynomial, or just infinite, right? That was the halting problem, right? Does it halt in a finite number of steps? That was undecidable. This is decidable because you can always simulate the computation and then stop after a polynomial number of steps and say, no, it doesn't accept it in a polynomial number of steps. So this is what Cook and Levin showed was NP complete. Basically, they showed that it was, they showed that this problem reduces to the SAT problem, right? SAT, remember, is satisfiability. SAT is given a logical formula on n variables, those variables x1 through L dots xn, right? Does there exist an assignment of the truth values that evaluates the expression to true or not, right? That's the satisfiability problem. Basically, they showed that you can take a computation of a non-deterministic Turing machine, encode it as a SAT problem, as a logic problem, and then the question becomes, well, does there exist an input that will evaluate to true? And this is actually not that difficult to show. Why? At the end of the day, what is a processor? It's a bunch of AND gates, OR gates, right? And usually NAND gates, right? A generalized processor, you have a lot of bells and whistles in there, but at the end of the day, what is it? It's just a bunch of ands and ors and nots, right? So it's not that surprising that satisfiability is NP complete, okay? So here's the chain so far, right? That you've got this, this canonically complete problem, reduces to SAT, so less than or equal to in math SF P time, to SAT, math SC SAT. Does that work? Uh-oh. Ah, they don't have that character font set. Text SC? Nope. Oh, wow, okay. So I'm going to have to do it like this. Sorry. It does, there we go. So that problem, the canonically complete problem, reduces to SAT. That was due to Cook and Levin in the early 70s. From that, we can now reduce to other problems. For example, I'm going to immediately reduce here to 3 SAT. 3 SAT. So what is 3 SAT? 3 SAT is a satisfiability problem where all expressions are CNF, which is conjunctive normal form. Yep. Oh, you've seen this before? Or in 235, where did you see it in 235? Oh, you probably had to do with SAT solvers, right?
Yeah, for all intersection at least, SAT was like our, I don't know, extra topic, I guess.
Okay.
We had like the main homeworks and then we had SAT homeworks.
Okay, so you did some like constraint satisfaction problems or something using SAT.
We used mini SAT.
Okay.
At one point, yeah, like it started off like a simple question, like is this satisfiable? And by the end it was like, is this pseudo satisfiable or something?
Oh, I don't know what that is. I'd have to look that up. Anyway, what we're going to simplify this down to 3 SAT, where it's actually 3 CNF SAT, where everything is in conjunctive normal form, meaning that you have a series of clauses, each of which is a disjunction, right? Ors, right? I'll write it like this, ors. And the expression is the conjunction. And in case you don't remember those, that's ands of the clauses. Right? Each clause only has at most 3 variables or their negations. Right? And it's not trivial, but it's not that difficult to see that you can take this big giant formula, a generic formula, and then you can factor things out, massage it, introduce dummy variables so that you can get it into this form. For example, let me go over here. Here's the one that we'll be working with. Where's 3 set? Okay, there we go. That's the one I want to work with. That's a 3 CNF, right? It has 1, 2, 3 clauses. Each clause is a disjunction, or. And then the entire expression is each clause conjuncted together, right? And. Each clause only has 1, 2, 3 variables, or their negations. So it's not, again, it's not too difficult to show that you can take any general form that you want, any general formula, and change it into a 3 CNF formula. Can you change it into a 2 CNF formula and make it even easier? No, because then that becomes solvable in P, right? If everything only had 2, right, and not this third over here, then it's actually tractable and easily solved in polynomial time. So this seems to be the threshold. This is as simple as it gets, right? And this is still NP complete. So again, what does the landscape look like here? Cook and Levin showed that the canonically NP complete problem reduces to SAT. You can show that SAT reduces to 3 SAT. What we're going to do now is show an actual reduction. R reduction is going to be showing that you can go 3 SAT down to, in polynomial reduction here, to click. There we go. Come on. There and there. Okay, that's at least a little bit better. Yeah.
So Cook and Levin showed that L and P reduces to SAT.
Yep.
So who found out about L and P?
Well, that's just it's a canonically complete problem.
Okay.
It's you come up with the definition and show that that any NP machine, right? Like here's the machine, here's the input. Does its computation lead to an accepting state? You can take that question and translate it into a bunch of circuits, right? And the circuits are and, or, not gates, right? And it makes sense because you can, again, what is a processor? It's just a bunch of circuits, right? Now it's extremely complex and there are millions of those circuits nowadays, but go back 50, 60 years and you only have hundreds of circuits, right? So it's not that hard to imagine that you can take any computation, translate it into a bunch of circuits, right? Because that's what we do, right? That's how computers are made, right? So we're going to go ahead and go from 3 SAT down to click. So now, what is the click problem? First of all, let's go ahead and come over here and look at an example. I don't have a ready-made graph here, but I'll go ahead and do it like this. All right. So now a click C, which is a subset of vertices, is a set of vertices such that for all x and y in the click, x and y are connected in the edge set. Right? So for example, let's highlight here. 1, 2, 3, 4. There's a click. Why? Because it's a complete subgraph. This is connected to everything else. This is connected to all the other green ones. This is connected to all the other green ones. Could I add in this into the click? No, because these two are not connected. Okay? So in other words, it's a complete subgraph. If you look at this graph, it's a K4, right? So that's what a click is. Everybody, clicky, a clicky group, they all know each other intimately. Everybody is connected to everybody else. The click problem is given a graph G and an integer K, does there exist a click of size K? Right? That's the decision version of the problem. Now remember that K can run from 1 up to the size of the vertex set here. Right? you will always have a trivial click of size 1, right? So if k were 1, you would just immediately answer yes. If k were 0, it's ill-defined. If k were v, right, the n, then you're basically asking, is this graph a complete graph? That would also be very, very solvable. Why? You just have to check how many, the size of the edge set. But for general k running from 1 up to v, this is an NP complete problem. Right? Now what we're going to do is we're going to show that reduction. That we can take a 3CNF formula, something like this, and we can transform it into a graph, something like this, and preserve those questions. That over here, this will have a satisfying assignment if and only if this graph has a click, right? And vice versa, that this graph will have a click of size k if and only if there's a satisfying assignment over here. Right? Now to do that, we're going to need a framework. I think that this framework is due to, now I forget their names. I looked it up right beforehand, but now I forget their names. There's this compendium of NP complete problems, and they propose this 5-step process, just like some books have proposed this 5-step process for analyzing algorithms. We've got this 5-step process for improving NP completeness. All right. The first step is that you have to know that it's an NP, right? If you don't know that it's an NP, right, you could have a problem way out here. Is it going to reduce down to something in NP? Very unlikely, right? In fact, if you did show that reduction, then what happens? Whatever complexity class is above all this stuff collapses down to NP, right? So we're not going to do that. What we have to do is we have to first establish that it's somewhere in this arena. Right? That's easy because all you need to do is come up with a non-deterministic polynomial time algorithm for it. Okay? Then you select a known NP complete problem to reduce to your problem, right? You're going from the known NP complete problem to your problem, right? It's not the other way around, right? You asked about whether or not it would be the other way around. Do we think that that's possible? Probably not. That would lead to a collapse, right? It is possible if you show that these both are NP complete, then after the fact, well, of course, by definition, it'll reduce down or reduce to the other one. But again, it's not down or up within this class here. These are all equivalent, right? They're all NP complete. Right? 3, you come up with a mapping reduction that maps yes instances of the first problem to yes instances of the second problem. Then 4, you show that that reduction is correct. You just need to prove it. And it's an if and only if condition. Then you show your reduction is computable in deterministic polynomial time. Right? So let's go through this 5-step process for the click problem. Okay? So let's go with 1 first. 1. We need to show that click is in NP. Right? If it's not an NP to begin with, then it can't be NP complete. Right? So here's my proof. All I need to do is come up with a polynomial time algorithm that uses non-determinism. Here's my input. It's going to be a graph G and an integer K. And my output will be except if G has a click of size K. Right. So here's my guess phase. Right. Guess a subset C equals V1, V2, dot, 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 Vk of vertices. You can guess that, right? So along the way, let's prove that this is going to be in polynomial time. This is order what? All you have to do is guess k things, or at most, go through all the vertices and guess. This is in the set, this is not in the set. This is in the set, this is not in the set. So at most, this is going to be order n, right? Order k, really. But k is bounded above by n. 2, verify. Right? For each pair, x and y in C, right? If x, y is not an edge, is it a click? They're not connected, so no. So reject. Otherwise, if you get through every single pair and they all are connected, then you guessed correctly. There's your certificate. This is your certificate of authenticity. It is indeed a click of size K. So we will accept. And that's it. Right. What about this phase right here? Again, this was the non-determinism here. This is deterministically verifying that it's a correct solution. This is going to be order what? For each pair. N squared, right? For every pair, right? Truthfully, it's going to be, since this is of size K, it's going to be K choose 2, which is K squared, about K squared, but then that's less than or equal to N squared. That's why we get this. Right? We just need to show that it's polynomial with respect to N, right? And we're good. All right. 2, select a known NP-complete problem to reduce from. Now, this is where the the artistry comes in, because generally you want to select a like problem for a like problem. Sometimes that's not possible, because if you want to show establish that first graph problem as NP complete, you may have to reduce, like we're reducing here, 3 sat to click. Right? Somebody did, yeah, at some point, right? Or maybe not. Maybe they did it from some logic problem to something else. This is easy. I generally show this one because it's easy, right? It's easy to visualize. It's easy to understand, right? Sometimes things are not all that easy. Like for a paper a long time ago, my colleagues thought that this problem that we were looking at was NP complete, and I thought, it doesn't look like it, but we didn't know if it was NP complete or not. And so, the restrictions that we put on it were too much. You can actually solve this in P, which means that, okay, it probably wasn't what we were looking for. So we came up with a different formulation, and I thought, yeah, that looks a little bit more like it. And then somebody else in our group showed the reduction, and okay, we made it as close as possible. We selected something that was as close as possible to the problem that we were trying to prove was NP complete, so that you just had to do a little bit of a tweak, and it turns out, okay, then that's hard. Unfortunately, that little tweak can sometimes make the difference. Remember, if this was 2 sat, where everything only had 2, then it becomes easy, right? There's a huge gap between 2 sat and 3 sat. One is polynomial, one nobody knows how to do it in polynomial time. And that's just one variable per clause. Right? Why would it make such a difference? Right? There are lots of problems like that, where there's one little tweak and it suddenly becomes difficult. Right? For example, Hamiltonian path. The analog to that is Euler path. Do you remember what an Euler path is? So Hamiltonian path is one that visits every vertex exactly once. An Euler path is one that visits every edge exactly once. An Euler path is very, very simple to solve, because all you have to do is check the degree of every vertex. Every vertex has to be even degree, except for the last 2 on your path. Then there exists an Euler path. But once you change that one little tweak from edge to vertex, it becomes super hard, super difficult. Right? All right, so this work is already done for us. But what I want to emphasize here is that you are going from 3 sat, something that is known to be NP complete, and you're reducing to something that is not known to be NP complete until after you're done with this proof. Okay? 3. Isn't it the... You come up with a mapping reduction that maps yes instances of the NP complete problem to yes instances of the problem that you're considering. So what I want to do is I want to map a propositional formula, phi, to a graph, G, such that phi on X is satisfiable if and only if G has a click of size k. Okay? Now here's the idea. Phi will have k clauses. Right? For each clause, for each variable, in each clause, we'll create a vertex. So here's a clause, C1, let's just call them what they are. X, clause 1, I, J, X, clause I, here, I'll label them as 1, 2, and 3. 1, 2, and 3. X, I, J, K. There we go, 3. Here's a clause, and it's a disjunction, so it's or. I should have given myself more room there. And all I'm simply going to do is output x sub I, x sub j, and x sub k. And those are 3 vertices now. Right? We do that for every clause. Okay? So if there are k clauses, then there are going to be k triples and 3k vertices total. Okay? Edges are drawn as follows. 2 vertices will be connected if and only if A, they are in different clauses, and B, they are consistent. In other words, x of I is not equal to the negation of x of I, right? If they're not negations of each other. The reason that we do this is I'm going to want to set one of these variables to true. If I set that variable to true, what happens to its negation? It automatically becomes false. And in these clauses, at least one of those variables is going to have to evaluate to true. Let's take a look at an example here. The example from before. Click to sat. There we go. Or sat to click, it should be called. I don't know why I called it that. All right. So I've got 1, 2, 3 clauses. Each one has 1, 2, 3 vertices. So in total, I'm going to have 9 vertices. So let's do this first clause over here. I'll label this as C1, C2, and C3. So here's C1's clause. X1, X2 negation, there we go, and X3. Right? Those are all of the vertices corresponding to that clause. Up here, let me do C2. That's X1, negation of X2, negation of X3. 1, 2, 3. There we go. And over here, I'll put clause 3. Right. X1, X2, X3. Remember, these are disjunctions. Oops. There we go. I don't know why, by what standards a circle becomes a square under this drawing program, but whatever. There. I've taken care of all the vertices. All right. There are 9 total because there are 3 clauses, 3 variables each. Now I'm going to draw edges according to these 2 criteria. They've got to be in different clauses. So in other words, I'm not going to be drawing anything between a given clause. All right? These are not going to be edges. Right? These are not going to be edges. Nope, none of those edges there. Yeah.
This is a 3D graph then?
No, well, I mean, what do you mean by 3D graph?
Well, there's the X1, X2, X3.
Those are just labels, right? So put a superscript up here. 1, 1, 1, 1, or 2, 2, 2, 3, 3, 3. I just didn't want to make the diagram more complicated than it is. Those are distinct vertices. What do you mean by a 3D graph? You can take any graph and draw it in 3 space if you want, right?
Well, but there's like 3 variables to the point. So
Well, each vertex corresponds to whatever is in each of these clauses. Granted, there are 2 negations of x2, x2. There are 2 copies of that thing, but they're in different clauses, this one and this one, so they're different vertices. And you can distinguish them by giving it another label here, right? 1, 2, 2, 2, 1, 2, 2, 1, whatever, right? Now, I'm not going to draw any edges within a clause, but I am going to draw edges between clauses as long as they are not negations of each other. So, for example, what about x1 to x1? Is that consistent? Yeah, because they're not negations of each other. Right? What about x1 to x2, x3? Yeah, those aren't even the same variables. So, those get edges. There we go. Now, what about well, here, let's go with the other clause over here. x1 to x1? Yep, that's, that's consistent. x1 to x2, x1 to x3. All of those are going to be consistent. Can I get it to do a... Nope. Oh, well. I thought I could do... I thought I could do that. Nope. Okay, that... Come on. I wanted to do a bit like a Bezier curve or something. It's not. Oh, whatever. All right, so what about negation of x2? It's going to go to x1 and x3 because those aren't even the same variables. But what about the negation to x2 to the negation of x2? Yes, that's consistent too. Right? So 1, 2, and 3. There we go. And then what about its relation over here? Well, those two should be pretty obvious because they're not the same variable. But what about this one right here? x2 and not x2, does that get connected to x2? Nope, because those are not very consistent variables. If I set one of them to true, the other one necessarily becomes false, and vice versa. Right? And that's going to screw up my, my encoding of this graph. What about x3 here? x3 is going to go yes, yes, no. Good. So, yes, yes, and then no. Right? That takes care of this relationship with clause 2. What about this relationship with this relationship? They're all going to be there. That one, and it's consistent with x3 here. That one. There we go. What about the relationship between this clause and this clause? They're all going to be there except for x2, not well, the other one, I guess. Right? This is going to be there. This is going to be there. This is going to be there. x2 will go to x1, but not to the original x2, but it will go to x3. Right? Not x3 will go to x1 and x2, but will it go here? Nope, because they're negations of each other, so undo that. Okay? So there is the construction. Step 4, you've got to prove that it's correct. That is, that it preserves these solutions, right? You've got to prove this statement right here, the if and only if. Right? So that's actually just by construction. It's pretty straightforward here. Instead of going through the full proof for time, let's go through and find a satisfying assignment to this. So first of all, ignore everything down here. Right? Give me a satisfying assignment for this thing right here. x1, x2, and x3. Okay, that's the boring one, right? And then does it matter what the other two are? No. So what does that correspond to in our graph over here? Setting x1 to true, x1 to true, x1 to true. Well, guess what? That's connected to that, that's connected to that, and that's connected to that. Right? So there is one satisfying assignment. Choose something more interesting. Yeah, go ahead.
one of them, all 3.
Exactly. for each clause, at least one of these needs to be true. So let's make it so that, I don't know, x2 is true. There we go. All right, that takes care of this clause, and that means that x2 would end up being true. But what about not x2, not x2? Those are not true. So that's not part of my click. All right? So what would I have to set the other two to get this to be true? Either one of them to 1, right? So 1, 0. There we go. And that means that this will be true, false, false. But that's okay because this is true. This is false. Uh-oh. Yeah, what do I need to do that? That needs to be 1, right? Which gives us almost the same thing as the first one, but a different click of size 3, right? So 1 would be, let's see, we can connect over here to this one, right? So that's also involved. And then x2, I already got that in clause 3, and then x3 is 1. So, oh, I have to, sorry, it's not that one. It would be this one, right? Oops. Is this true? Let's undo this. 0, 0, 1. Is that? Yeah, that'll be okay. Why? This is true. There we go. And now assigning x2 0 means that this ends up being true because it's a negation, and this ends up being true because it's a negation, and that's going to give us this click right here. There. X3 right here. Right? X3 is true. X2 is false. Therefore, its negation is true. True, true, true. Right? Which forms a click of size 3. Right? So the full proof is in the book if you want to take a look at it. All it is reasoning that by way of this construction, right, you can work both ways. Now you do need, if it's an if and only if statement, so you do need to prove both ways. That given a propositional formula here that is satisfiable, right? It's satisfiable implies that there is a click of size k. Then you need to work the other way. That if you have a click of size k, through this mapping, you can go back to your propositional formula, and it will be satisfiable. Right? Okay. So 4 omitted, but that's the hand wavy version of it. 5, right? You have to show that this reduction is computable in deterministic polynomial time. Is it? Well, here's the outline. The outline is basically an algorithm, right? So for each variable in each clause, you'll create a vertex. How many vertices are you creating? 3k. That's going to be order 3k, which is order n. Right? 3n, n. Okay? What about outputting edges here? Well, if you've got a polynomial number of vertices, then clearly you're going to have a polynomial number of edges, right? N squared, right? Because for the complete graph, you would go through and ask, should this edge be there or not? Should this edge be there or not? And all you're doing is applying this criteria each and every single time, giving you at most order n squared. And it's deterministic, right? If I gave you this clause right here, all you'd have to do is output these 3 things, and you're not guessing anything here. Right? So that proof, right, see other part. Right. Then, I mean, the construction is straightforward. Right? So what we've shown today is that reduction. 3 sat reduces to click. Oops, sorry, up here. 3 sat reduces to click. So let's take a look at our landscape so far as the last item for the day. I'm going to give myself way more room than I need to because we've got an entire chain here. Down here is P. up here is NP complete, right? And then this is all of NP. Again, the very starting point of all of this was Cook-Levin, showing that the canonically NP complete problem reduced to SAT. We didn't show it, but it's not hard to see that this can actually reduce down to 3 SAT, right? 3 CNF SAT, where everything is in a very, very particular form. It's called conjunctive normal form. This is actually all over the place. You can do a lot of logic stuff, and it's usual to take some logic and put it into a normal form so that everybody is speaking the same language. Yeah.
So SAT doesn't mean once.
SAT.
Once.
Yeah. What does one SAT mean?
Just a whole
One SAT
condition.
would just be like x1 and x2 and not x3 and ... right?
Yeah.
So I mean that's trivially easy. All you need to do to see if it's satisfiable is what? Make sure that no variable and its negation is there, right? So you can have x1, x2, a negation of a variable, but you could never have x3 in this ever, right? We call this, what do we call this usually? One SAT, a for loop, right? In other words, for all x, right? The x, there we go. All xi, right? And what are you doing with this? Why is this a for loop? For each x in your set or your universe of discourse or whatever, right? You're going x is equal to x and total is equal to true, and so total is equal to x and total, right? In other words, for all a universal quantifier. Yeah.
So SAT doesn't put a constraint on how many variables.
No, I mean, n variables, right? Now, I mean, if you get too many clauses, if you get too many disjunctions, then you become trivially false, right? Then it becomes a contradiction, because if you have x1 and then not x1 too many times, then they're all going to contradict with each other, and that's when you get a contradiction. In fact, that's the opposite of SAT. What would it be? Taut, right? Tautology, right? Instead of, does there exist a truth assignment such that phi sub x is true, a tautology is going to be for all x, right? Phi on x is false, right? Or tautology, does there exist for all? Yeah, for true, sorry. What am I saying? There we go. Is it a tautology, right? For all truth assignments, does it evaluate to true? Now, again, what would you have to do? Brute force, generate the entire truth table. If the entire columns is ones, then yes, it's a tautology. It doesn't matter what your truth assignments are. Yeah, this is NP. In fact, it's NP complete. This is a class called co-NP, right? And it's co-NP complete, right? It looks like this. Here is P, here's NP, here's co-NP, right? There's co-NP, there's NP complete, there's co-NP complete, and where is P in all of this? Somewhere in their intersection, right? Now, are there things in here? Are there things in here? Are there things in here? Or is it the case that NP is equal to co-NP, in which case all of this stuff collapses to each other? Now, that still doesn't answer the P versus NP question, right? But it's another question entirely, right? Yeah.
But so people haven't proved that there's algorithms in NP complete that can be solved by P. But people have to prove that there's algorithms in NP can be solved by P.
No, I mean, well, sorting is trivially an NP, and it can be solved in P, right?
There's no like.
We don't know if there's something. Well, We don't know if this is empty or not. This could be the empty set, right? If it's the empty set, then this entire thing collapses down to P.
So are there like previously thought to be NP questions?
Good question. For many, many years, primality testing was not known to be one way or the other, right? And then 20 years ago, somebody showed that, in fact, a group of grad students and their advisor showed that, no, here's a deterministic polynomial time algorithm that determines whether or not something is prime or not, right? Now, that's completely different from factoring something, right? Here's, for example, breaking RSA crypto system and factoring those two things out. Asking whether or not something is prime or composite is completely different than, all right, we know that this is not prime. I want you to give me its prime factors, right? That's completely different. That is who knows, right? But it's not really a decision problem. You'd have to translate it into a decision problem to ask that question. And is it NP complete? Probably not. But is it in P? Hopefully not, right? So is it somewhere in between? Oh, hopefully, right? Right? Because if it was shown to be NP complete, then that wouldn't be too groundbreaking. It'd be surprising for various reasons, but it would not break cryptography or anything, right? I don't know. There might be some consequences that I don't know of, but yeah. All right. Back over here. All right. So here's our chain so far. All right. That we go from the canonically complete NP problem to SAT to 3-SAT, and now in the world of graph theory here, we've got a click problem. All right. On Monday, we'll go ahead and reduce this further to a vertex cover problem, right? And that will be Monday. And then then Wednesday we'll use that for a review. But otherwise, you can see this chain of reductions, right? Now, is it true that you can go from vertex cover back to this? Yes, by definition. You don't even need to show this, right? But is it true that you can take, say, vertex cover and reduce it down to something down here in P? You just proved that P is equal to NP, right? What about the other way? Could you show that this is not possible? Right? If you did, guess what? You showed that P is not equal to NP. Right? Either way, you've solved the $1 million question, right? And just that easy.
Can you do something like something that reduces click without work, prove that it's
You could take click and show that it reduces down to, I don't know, Dijkstra's.
or maybe no, if like wanted to prove algorithms to be NP complete.
Well, you remember, it's not algorithms that are NP complete. It's problems that are NP complete. So if you've got another problem over here, I don't know, 0-1 knapsack, right? You could take any of these problems and reduce it to 0-1 knapsack, and that would establish that 0-1 knapsack is NP complete. For example, you could show that click reduces to this, right? We won't do that because I don't know how to do that.
You do it the other way?
By definition. Yeah, either way would work, yeah. Yep. But starting out with a problem of unknown, if all you've done is shown that A is in NP, you don't know if it's NP complete or not. If I show that A reduces to, say, SAT, right, that's not really saying anything, right? You already knew that because of the definition of NP completeness and Cook-Levin showing that SAT was already NP complete, right? It's trivial that sorting reduces to anything because that's the definition. That doesn't show anything, right? That just shows that the definition again, right? It just shows that 1 + 1 is 2, right? You have to take a known NP complete problem and reduce it to your problem to establish that it's NP complete. Right? Yeah, showing the other way doesn't say anything. Right? You can always reduce trivially from, I don't know, shortest path to longest path. It doesn't make any sense. Right?
Is there like a significance to application significance to NP and NP complete?
Well, once you've established, like, 0-1 knapsack problem is NP complete, should you try to brute force it? No, because that's exponential.
If you haven't established that.
If you have not, well, then either you come up with an algorithm, and if that algorithm runs in polynomial time and it solves it exactly, you've just shown that it's in P, right? Now, if you additionally show that it's NP complete through some mathematical magic, you've just shown that P is equal to NP, right? Which you're not doing that. Crackpots do that all the time. They'll publish so-called proofs all the time on like Archive, or they'll just the one last thing I'll say on that is that the first sniff test, does it smell, is what was it written in? Was it written in Word? If so, it's probably wrong. If it's written in LaTeX, oh, okay, well, that passed the first test. Let's go ahead and look at this seriously. And then you get into technical arguments of, does it relativize? Because there are like 3 or 4 different hurdles that people have established that, well, if you're going to try to prove P versus NP, you're going to have to resolve this other question over here, which just seems just as difficult, right? How did you circumvent that, right? And if you didn't, or you didn't even address it, that doesn't pass the sniff test. All right, have a good weekend.